So hi everybody, my name is Lee. This is some work that I did with John Kelly and Tim Barfoot on getting a visual teacher to work with monocular vision. So why monocular vision? So it turns out there are a whole bunch of vehicles out there in the world that have monocular cameras that were originally designed for things like teleoperation. And there are a bunch of situations where it would be useful if these vehicles could do some manner of autonomous navigation. So you can think of things like bomb disposal robots that were designed for teleop, where maybe you want to drive them manually to some location that's dangerous and have them come back on their own. You can think of quadcopters with a single downward-facing camera that maybe you want to have them do some sort of controlling maneuver autonomously. Or even something a little bit more business-like, like a telepresence robot with a webcam that maybe wants to navigate repetitively between different rooms in an office. So these robots are out there, and it would be great if they could do these repetitive navigation tasks autonomously. And one really elegant way of doing it is through visual teach and repeat, which I'm sure all of you have heard plenty about. But just to recap, in case anyone's not familiar, visual teach and repeat is this autonomous vision-based route following system that's been under development in Barfoot's lab for many years now. This is just a video working at Canadian Space Agency last year. Essentially works by you drive the robot along a path manually and capture a bunch of images, make a map out of that, and then localize against it in a repeat pass. So since the next two talks are both teach and repeat talks, I just want to provide a bit of context for both by going over just at a high level what the system architecture looks like. So as I said, there's two phases, a teach phase and a repeat phase. During the teach phase, you are driving the robot manually along some path and capturing images from some vision sensors. So this is typically done with a stereo camera. There have been extensions to three-dimensional LiDAR, Kinect cameras, and also binocular cameras, obviously. So with these images, you can detect and track features. We use surf features in our version. Use these to get relative pose estimates using some digital odometry algorithm. And then you can keep track in a pose graph of all the different digital odometry estimates that you come up with, and also the features that you use to compute them. So you get this database from the teach pass. And then in the repeat pass, you use pretty much the exact same localization procedure. So again, you're capturing images from your vision sensor, tracking features against them to get relative pose estimates. But then we're also localizing against this map that we built up in the teach pass. And what we do is we basically have a window of keyframes around where we currently are in the path, and we do a bundle adjustment over that window to get a very accurate metric local map of where we are and localize against it down to the centimeter. So you can project your 6-degree freedom pose from that procedure down onto some local ground plane and do path tracking against it. The path tracker that we use actually controls for two things, the heading error, so which direction you're pointing along the path, and then also the lateral path tracking error, which is how far off perpendicularly you are from the route. So I wanted to zoom in a little bit on this localization pipeline that I mentioned, which is used for both the teach and repeat passes. Go into a little more detail about it. So in the original stereo pipeline, it starts off with a pair of stereo images, obviously. We do some pre-processing on them to dewarp and rectify them according to the calibrated camera model, detect surf features in them and track them, match them between the stereo pair. And once you've done this, you can triangulate them into the world in 3D using the standard stereo equations. We can track those either against the previous frame if we're just doing a stereo VO, or against the current local map if we're doing the repeat pass localization. And this gives us a set of feature tracks that we can stick into a 3-point ransack algorithm to generate hypotheses for the motion and also reject outliers. The remaining tracks that are left over from that process go into a Gaussian optimization process that finally spits out a combined pose estimate. So that's the original stereo pipeline. And one of the important things that we're doing in this work is to actually do a comparison between the monocular pipeline that I'm going to talk about in a second and the original stereo pipeline. So to do this, we wanted to keep the back end totally consistent, leave all the optimization stuff alone, and just come up with an alternative front end to do the vision stuff. So now we just have a single monocular image coming in. We're doing the same pre-processing, same feature tracking stuff, except we have this extra depth estimation magic block that somehow turns monocular points into three-dimensional points. So how do you do that? There are a bunch of different ways in the literature, obviously. Everybody's familiar with Andrew Davison's fantastic Monoslam from several years ago that does everything in an extended Clement filter. You can imagine doing a bundle adjustment type procedure as well. But there are problems with these that we don't particularly like for our application. Typically, monocular slam algorithms are intended for sort of handheld cameras that you can control the motion very nicely and make sure you're reobserving a bunch of features to get a really good set of constraints on the depth. We're operating on ground vehicles typically, so our motion is more constrained. Depending on how fast you're going, the frame rate of your camera is, it can be difficult to make sure you get a lot of good observations. Another problem is that since we're actually controlling for lateral path tracking error, which is a metric quantity, we actually need consistent scale factor in our slime solution, which you don't always get from the monocular solution, unless you make assumptions about the environment. So what we decided to do instead of the full slam problem here is just make the most simple assumption we could think of, which is to pretend that everything in the world is flat around us. So instead of actually trying to triangulate 3D points in the world, we can just project them onto this local ground plane that we carry around with us and get the depth from that. Which is simple, but actually it goes a lot further than you think. So we can do this just by carrying around a few different coordinate frames on our robots. There's a camera frame that we're trying to estimate the depth in. There's a vehicle frame that's just the body frame of the vehicle. And then finally a ground frame that we can define pretty much anywhere we want. For a ground vehicle, it's just the footprint of the vehicle where the wheels are touching the ground. If you wanted to put this on a quadcopter, for example, you could look at, say, the altimeter and the orientation sensor to figure out that transform. So the observation model, you can imagine all the Z components in the ground frame are 0, transform that into the camera frame, and just do your standard projector geometry to get it into a crystal coordinate in your actual camera. And since it's only 2 equations and 2 unknowns, you can actually solve for everything really easily. So if you just do this really naively, it's actually pretty good for just doing 3-degree of freedom visual odometry, but it didn't work out so well for the mapping components. So we needed to add an extra piece, which was actually an uncertainty model on what the ground actually looks like. So the idea is that it's not perfectly flat, but close to us, if our wheels are touching the ground, it's fair to assume that it's pretty close. So one way we can deal with this is by looking at the transformation between the vehicle body frame and the ground frame that we're carrying around, and just modeling it as a probability distribution with a mean and a covariance. So you can think of sort of the underlying covariance matrix here, which has 2 dimensions corresponding to the noise on your camera, and then another 6 corresponding to how uncertain you are about the ground plane. You can figure out the Jacobian of your measurement model with respect to these things, and just do the standard linearized propagation to figure out a Gaussian distribution over your 3-dimensional feature in the world. And graphically, for just sort of an evenly spaced grid of features, it looks kind of like this, and as you'd expect, stuff further away is less certain. So that's sort of the gist of the monocular pipeline. The rest of this is going to be about the field testing that we did. Specifically, we had 2 things we wanted to try out. One thing was to actually characterize how this pipeline would actually work in the system in a bunch of different conditions and over some pretty long routes. And also we wanted to compare it against the original stereo pipeline using the same hardware and the same routes to see how it stacked up against the original system. So we did this by using the stereo camera in both cases, but just taking the left image. So you can think of an eye patch. So hardware-wise, what we had was a ClearPath Husky rover, a Bumblebee FP3 stereo camera that was mounted about 1 meter off the ground and measured for an angle downwards at 47 degrees to the horizontal. We just measured this by hand. The calibration doesn't need to be super accurate because of all the uncertainty that we have in our transforms. Standard Ubuntu ROS computation system. And for ground truthing, we actually had 2 setups depending on whether we were operating outdoors at Vitalis or indoors in our Mars Dome, which we'll hopefully be visiting for the tech tour later this afternoon. So we just had an RTK corrected GPS system outdoors that got us centimeter level accuracy and a fancy new Leica multi-station that does laser tracking indoors to get millimeter accuracy. So this is the outdoor route that we came up with. It's a 1.4 kilometer drive around various parts of Vitalis. There's some different terrain types, grass, gravel, sand, parking lots with varying degrees of texture. And the procedure here was that we would drive the vehicle along some route manually, record the stereo data, and then use that exact same video sequence to train both the monocular and stereo pipelines, and then try and repeat it both ways. And you may not be able to tell, and that's kind of the point, but there are actually 3 lines on this plot. They are the same to a large extent, which is good, because that means that all 2 of our systems are performing pretty much the same and doing very accurately compared to the teach pass. But if you want to look a little bit more quantitatively, we can take a look at the lateral path tracking error, which is, again, how far off to the side you are from the path, and look at it for both the monocular and the stereo cases. So the green lines in these plots are the lateral path tracking error that we got from our GPS measurements, so the true lateral path tracking error. And the blue and the red lines are the estimated lateral path tracking error that our systems are actually using to control the vehicle. So you can see that, except in a couple of places where the monocular pipeline breaks down, and I'll talk about why that happened later, the actual lateral path tracking error recorded by the GPS is very similar for both cases and gets centimeter level accuracy pretty much all the time, which is great. And also even the estimates when localization is working properly are very consistent as well. There's one case where there's a manual intervention, and again, I'll talk about that later. But for the most part, when it's working, it works really well. But that was kind of an easy route, because most of it's flat outside, and there are a huge number of non-planarities to mess up our assumptions. So we tried to do something more complicated inside the Mars Dome, and drove a shorter but more difficult route that had a lot of very nonplanar features, like really big bumps that were sort of the same size as the robot, some side slopes, valleys that clearly violated our planarity assumption, some ramps, and also some hills. And again, you can see the performance for both pipelines is pretty much identical in both cases, at least until you look at the autonomy rates again. And then we find that in the dome, the monocular pipeline didn't have as easy a time at localizing as the stereo pipeline, but when it was working again, it performed with the same level of accuracy. So there are actually 3 cases in the indoor route that required manual intervention for a couple of meters, and again, I'll talk about why that happened in a sec. So we did these routes a bunch of different times, totaling about 4.5 kilometers of navigation for each pipeline, and found that for the outdoor stuff, the mono pipeline, except in one spot that it pretty consistently had trouble in, performed just about as well as the stereo pipeline, whereas the stereo pipeline didn't fail at all. In the indoor case, it was a little bit different, still about 90% autonomy rates all the time, but not quite as robust as stereo. So the obvious question here is, well, why were the monocular autonomy rates so much lower? And it turns out that it didn't even have anything to do with the roughness of the terrain. Actually, some of the most challenging features in the Marshstone were the parts where the monocular pipeline did the best, which was kind of surprising. But where it actually broke down was in these kinds of cases where you have a lot of motion blur in the Marshstone due to just lighting being really poor. Or the one place that it broke outdoors was actually on a sort of freshly paved parking lot where the terrain was very similar to itself and didn't have a lot of strong texture in it. So the thing that these have in common is that they make feature matching very difficult, which is what we're relying on for localization during our repeat passes. And stereo is not immune to these things either. Surf matching is sort of independent of what you're actually doing with it afterwards. But what made it difficult for monocular is that we had all this extra spatial uncertainty in our pipeline, that you can think of it as sort of expanding the bubble in which we have to search for candidate feature matches. And so if we're coming up with a lot of ambiguous feature matches, then we're going to have a hard time choosing which is the best one, and our localization is not going to work out so well. So that was the problem. So just to sum up, we've shown that the clock ground approximation is actually pretty good for doing high accuracy monocular route following, as long as you have an appropriate uncertainty model to account for the fact that the ground is not completely flat. In terms of comparing it against the stereo pipeline, we found that when it's working, it's actually working just as well as stereo, but it's a little bit less robust in cases where feature matching is difficult. And it's reasonable to think that we could probably get around some of this by doing a better job of modeling what the uncertainty should be in those cases. And the way it's set up right now, the way that we handle the uncertainty is just through a bunch of tuning parameters corresponding to each of the degrees of freedom in the transformations. You could think of doing some sort of learning approach to actually try and figure those out online and improve your localization in those cases. The upshot of all this is that monocular robots can now do visual teach and repeat autonomously without any additional sensors, just with a simple software upgrade, and we think that's a valuable contribution. So that's all I had. If you have any questions, I can take them now. Otherwise, find me later, and also go to the tech tour. It's going to be good.
Do you have any questions?
Thanks. I guess it wasn't clear to me like what exact features you were using, but one thing that we have found, especially when we're using like monocular slam techniques like LSB slam and variants, that especially if you have like between 15 to 30 FPS and depending on how much incremental baseline you're getting, like direct methods can really help you in getting your pose like, because all you have to do is align two images together using just the gradient intensities instead of having, like, especially in the kind of like featureless environment you're working in. So I would be very curious to know if you have thought about like, trying a direct method, but under the assumption that you have enough frame rate and small baselines.
Yeah, so our system uses surf features, and we stuck with that just for consistency with the stereo pipeline. We definitely have thought about doing this with direct methods. It's not 100% clear to me if so we're operating at 15 frames a second just because that's the maximum that our camera can put out in this configuration. It's not entirely clear to me if that would work that well for direct methods, but we've definitely thought about trying it.
It has definitely worked for us at 1 meter per second average velocity at 15 frames per second. It seems to work pretty well, especially if you have an IMU to help constrain the like motion like you would do prior.
Right. I mean, the trouble is that we're trying to avoid using digital sensors. Which is
I see.
vision based.
Okay.
We'd like to avoid the IMU. Fair. Yeah.
I can just shout. Can you hear me?
Yeah.
The Gaussianity model, can you comment on, do you have any sense on how well it really fits? Obviously, sometimes it's not going to be true, like I guess on this ball. And yet I can't imagine anything better, but any empirical data on how realistic it is?
Yeah, we didn't do any particularly good analysis of how the ground varied compared to where the wheels were touching. It's not entirely clear to us. We mostly chose the Gaussian model just for analytical niceness. Kind of the standard thing to do. But I agree, like it would be good to do a much better analysis of this and maybe see if it's biased or has a long tail in some direction.
But you said you weren't too sensitive to it anyhow, right? As long as it was roughly.
Yeah.
Guess thanks in the interest of time, if we're putting on research now.